Hi, I'm Dragasuriu. I'm the conference organizer for CanSecWest, and the guy who started the Pwn2Own competition. We've been doing the PACSec conference in Tokyo for the last 17 years now, since 2004. And this year, obviously, we're going to be moving it online. But we're going to be experimental. We've got some challenges in the online format, some limits to engagement and interaction, but we're going to be trying to overcome those challenges and take advantage of the opportunities, the freedom of accessibility, the lack of travel, the lack of venue restrictions, and freedom for scheduling that we have in the online format. We're going to be doing VR meetings, live streams, stream out the Pwn2Own competition, and we're also going to be offering dojo training courses for the first time in a long time at PACSec, taking advantage of the global accessibility that we have with this conference. At PACSec Online this year, along with our new dojo training courses, we're trying something new, and we're going to be offering a free 2-day training course on September 23rd and 24th. It'll feature our dojo instructors giving excerpts from their longer dojo training courses, getting you some excellent free training on a wide variety of topics, and letting you get a feel for which one of our dojo courses might be right for you and your knowledge enhancement. Amongst the topics that we're going to have in our training courses this year include securing your legacy applications written in COBOL, effectively using threat intelligence, extracting and reversing firmware and writing ARM exploits, assessing and exploring your industrial control systems, developing exploits for the baseband processor in your phone using SDR attacks, locking down your Cisco networks and environments, assessing your IPv6 network security using the powerful escaping tool, making your security training more effective by making you a better trainer, attacking and defending your cloud instances and your Docker and Kubernetes containers. I hope we'll see you on September 23rd and 24th for this excellent free training, and later on at PACSec in November. Come sign up at secwest.net. So now it's time for this week's tutorial stream. This is going to be a talk from CanSecWest this year, done by one of our dojo instructors, Saumil Shah. And he uses a tool that he developed for emulation of ARM architectures in his course. This is an open source emulator that lets you extract firmware from a device and run it in the emulator, connect debuggers to it, instrument in all kinds of ways. It's really a boon for exploit development and analysis of security of embedded devices. And he has open sourced this tool, and he's done this talk about explaining how to use it, and it's a pretty powerful methodology. Please enjoy and learn.
Ready? Okay, great. Ladies and gentlemen, good afternoon. I wish I could have been there with you in person, but this isn't bad either. I think hanging out in the lounge and the locker room and the main track room for about an hour, I kind of felt like I belonged. Okay, let me share the screen and see how this thing goes. Right, share the screen. Share it. Okay, let me now maximize my presentation. Right. So I'm going to talk to you about a few little tricks that I've been working on the past year. This is one such project which kind of started turning out right for a change. I've been working on this for about 2 years, and late last year I released the first prototype of ARMX. Today I'm going to take you through what is ARMX, what have I done with it, and what can it be used for, and what are the roads ahead. I will then open up the floor to questions and answers. You can comment about the stuff that I've done. The entire project is open source. Yesterday, I made some updates on the GitHub, pushed it up to the latest version. And I also have a preview VM that you can download and play along. Right, so my name is Saumil Shah. I've been doing this ever since Jeff Nathan knows me, since a very, very long time indeed. And that predates me knowing Dragos, by the way. All right, before I begin the actual presentation, first a word from our sponsors. In India, we greet each other by namaste, folded hands, no contacts, and social distance. So respect to one and all, welcome. Right, so let's see what RMX is. The TLDR of RMX is, it is basically a bunch of terribly written shell scripts around QEMU, but it ends up doing something really useful. I'm calling it an ARM firmware emulation framework. The origins of RMX were basically, I wrote RMX to help me with my own class. I started teaching ARM IoT exploitation a few years ago. From time to time, I've always felt like having a virtual IoT device. So I thought, okay, there's nothing like, VirtualBox for IoT or VMware for IoT. So let's try writing one. Turns out it's not very easy, but this was the ultimate goal, was to kind of get as close to an IoT VM as possible. In the process, I learned a lot of things. Why do we need an IoT VM? Well, why do we need a VM? We should have a system that we can build and destroy at will and bring up without too much trouble. So I've used this for runtime analysis, reverse engineering, exploit dev, fuzzing, and just for basically learning more about IoT and the embedded hardware. There's no greater struggle than you trying to emulate missing pieces of hardware and fiddle around with QEMU. You better know that hardware inside out. And since we're not Fabrice Bellard, we better know the QEMU invocation options as well. So these are some screenshots from the RMX preview VM. When you start up RMX, it gives you a nice little menu. In the menu, you can see there are a few devices that you can emulate. Gives you a nice option to click and choose which device you want to boot up. And then as you go through it, it will create a virtual instance of, say, a D-Link router or a Netgear Nighthawk router or an IP cam or whatever have you. And as we speak, I'm tearing apart more ARM-based IoT devices and pulling off the firmware and emulating them inside RMX. A few points to be noted. This currently works for only ARM CPUs. By the way, there's a MIPSEX on the way as well. A few students of mine are starting to contribute to the project. And with any luck, we'll get MIPSEX released hopefully by the time the epidemic is over. So far, I've had successes emulating Linux-based OSs on RMX. I have not tried my hand with other OSs. Anyway, more on that later. Why am I jumping the gun here? Okay, first let's look at what's inside an IoT device. Basically, it's just a very specialized computer with a very specialized set of parts. But at the core of it, it's still the same, right? You still have the SoC, which has the CPU and the hardware. On top of the SoC, you have a kernel running, typically a Linux kernel for the most part. And on top of the kernel, then you, of course, when you boot into userland, you have a small file system, userland processes, and then all this dark blue stuff are basically the custom application that is layered on top of a typical Linux system. Right, so usually the software on these devices is coded up rather terribly. And the reason is not because of just sloppiness, but because you don't make money by selling software on IoT devices. You make money by selling number of units. So really there is no impetus to improve the quality of software on an IoT device, especially when that software is not visible. Like, how many times have you logged into your Wi-Fi router at home? Only when a guest arrives and you've forgotten the password, and then you need to reset the password and give it to the guest, and then you forget it. If the software is not visible, it is just forgotten and sits in the background. You configure it once, maybe it's a pain to configure, but once you get done with it, then you just don't pay attention to it at all. So there is no real impetus for manufacturers to improve the quality of software. In fact, you'll be surprised, well, or rather not surprised, that the kernel that's being used on typical IoT devices now are essentially kernel 2.6 back from the ancient years. Like I say, kernel 2.6 is the IE6 of IoT. It's never going to go away. It'll be there forever. So anyway, let's see what goes on. A few differences between a typical computer, a desktop computer, and an IoT device is the fact that your desktop computer has a lot of luxury. You have a spinning disk or a solid state disk. Now you basically have a block device which is really fast and has a lot of space. You can address it and read and write at will. You also have a lot of fast memory on board. But when you're looking at something like a little IP cam, you don't have that type of luxury. You have a very limited flash memory. The flash memory is not writable at will. It is basically flashable, and you can only flash it a few number of times before the damn thing becomes a CD-ROM. The file system essentially lives as a read-only file system, which gets mounted as a RAM disk after the kernel boots up. All I/O, all read and write that happens in the RAM of the IoT device. And then your logical question might be, so okay, how does that device achieve persistence? Where do I save my network settings? Where do I save my SSID? Where do I save my password and things like that? So turns out there is a small portion of flash memory which is writable, which is the NVRAM. And there is a shim which invokes a driver, the NVRAM driver. And whenever you want to persist something, you basically access the driver and write pieces of data onto the NVRAM. You typically store key value pairs on the NVRAM just for your important settings. And this is how persistence is achieved. Everything else disappears when the power is pulled off. Nowadays, devices are coming up with better, with more writable storage. Like you can plug in an SD card or an eMMC and write more to it. But still, the NVRAM way is largely followed, even in modern IoT devices. When we're trying to emulate the device, let me show you the boot up process first, and then we'll talk about how the device is emulated. Let me switch over to my VM. So this is my virtual machine for the ARMX virtual machine. I have a ARMX launcher. I'm going to click it, and this shows you, this gives you like the initial menu. I'm going to try and enlarge the fonts just to see if oops, can't seem to enlarge it. Never mind. Okay, forget the enlargement. I can now select a device. Let's say I select this, let's say I select the IP camera, and I click. And you can see the kernel booting up. This is a custom compiled kernel and the kernel will drop you into this ARMX console. Keep this in mind, and then I'll walk you through how typically an IoT device boots up. And then what do we need to do to emulate the same process in ARMX? So now let me go back to my slides. Here we are. So initially, when you power on, the CPU kicks in, jumps to the entry point, etc. All this purple stuff that you see is basically on flash memory, and this is part of the firmware. The firmware is populated as partitions on MTD, which stands for Memory Technology Device. Fancy way of saying flash memory. And you have several partitions, like you have the bootloader, which would be a U-boot or a U-bootish clone. The Broadcom devices have something called a common firmware environment. And there's some custom hacky bootloaders that devices used. But essentially, the CPU kicks off the bootloader kicks off the kernel. The kernel lives in its own partition, typically as a Z image or some version of it. And then the kernel starts searching for all the partitions. It searches the MTD partitions, and then when it finds the root partition, the root device, it will then proceed to mount the file system. Now the file system is stored in a compressed form because space in the flash device is always at a premium. The file system is compressed. The kernel will uncompress and mount the file system in RAM disks. So all the blue stuff that you see on top of it all happens in the RAM. Once the file system is mounted, then the control passes on to the user land. The kernel is pretty much done, and the kernel invokes the default process, typically, which is sbin init or whatever it may have been designated to. Sbin init will invoke a flurry of init scripts. These are all awfully written shell scripts, horrible spaghetti code. Every vendor does things differently. But what these init scripts do is they will build all the configuration files required for the system services and required for the applications. All these config files are built up on the fly by accessing values stored in NVRAM. So it's like say, okay, let's pull up all the network config and we'll write like etc network interfaces. Let's pull up all the DNS config and write etc dnsmask.conf. Let's write the HTTPD configuration. All these are written on the fly in the RAM disk. And that's why your router blinks a lot before it basically boots up. It's because all the init scripts are pulling these values from NVRAM, writing the config scripts. Once all the config scripts are written, these init scripts end up kicking off the services. First, the essential services kick off, like the networking subsystem or the USB subsystem, IPv4, IPv6, DNS. And then on top of it, once all your system services are done, then the startup scripts invoke the application that the device is built for. And at this point, your device is ready to be used. Now, when we're emulating the firmware, what we're going to do is we're going to grab a copy of the firmware, which is basically all this purple part. This is the, let me see if I can highlight it. Okay, no worries. We're going to grab the firmware, which is all the purple part. We're going to unpack the firmware and then populate it within our QEMU container, pair it up with a kernel, and then try and somehow virtually invoke the kernel. The kernel should then jump to the init scripts, which are now residing in an unpacked file system. And once we get a few things duct taped together, hopefully we get the init services and the applications up and running as well. So now I'm going to show you how the emulation game works. We're working with QEMU at the core. QEMU allows us to define some hardware, like you can get the basic hardware like your Ethernet or storage or the networking subsystem and other such things going. But QEMU does not have fancy hardware. Like QEMU does not have, if you're emulating an IP camera, a QEMU may not have a video device. If you can configure your existing webcam and interface it with QEMU, that's great. But I'm still struggling with all the libvirt stuff. I'm yet to master the art of defining custom devices in QEMU. So typically what I'm working with right now is just the basic emulation boards that QEMU defines. QEMU provides like a few emulation boards like Versatile PD or RealView or Versatile Express. And then you get to work with whatever hardware you have in that. When it comes to the kernel, what you can do in an ideal world is take the kernel that you extract from the firmware itself and then make that kernel boot up in QEMU. This would be an ideal situation, but it rarely happens this way. The reason is the kernel from the device is compiled with device specific hardware. And if the kernel does not find that specific bit of hardware, it'll either panic or it'll freeze or something weird happens, and we have no luck in QEMU. So for us in RMX, we have to compile the kernel ourselves, but we have to compile a kernel that matches the version of the kernel as close as possible to the one that is provided in the device. So like the IP cam that I'm emulating uses kernel 2.6.28. And what you do is you have to get a source of kernel 2.6.28, cross-compile it for ARM for that particular make of CPU. The IP cam uses like an ARM v5 CPU, seriously old. Once you've got that kernel compiled, you might have to suffer a little bit of makefile errors and toolchain errors, which can take up anything from 2 hours if you get lucky on Stack Overflow, or it can take up to 2 weeks with serious head injuries caused against the wall. After the kernel is done, then you can choose to create your kernel boot string, like the proc command line, and then hand over control to the init scripts. Basically, the init scripts are going to be a part of your uncompressed file system. The init scripts will need some NVRAM support, which currently RMX provides. For RMX, I had a mini breakthrough and was able to create an emulated NVRAM, which works in shared memory. So I can preload the NVRAM with key value pairs before starting RMX. It stays in shared memory. And then when it boots up, any access to NVRAM will be mapped to the shared memory, and the system can actually pull out the correct values from NVRAM. So effectively, the init scripts go through, the config files are built up, and then if luck holds out, then your services will start up and your applications will start up. Sometimes you have to fake some missing hardware. Like if a binary is looking for a video device and it doesn't find one, then either you have to just like touch a video device in the dev tree, or you have to do an MK nod, or in the worst case, sometimes you have to like LD preload a library and fake some IOCTL calls and intercept them. But all that is custom stuff that we will talk about later. But once this happens, we're good to go. So how do we create this stuff? I talked to you about custom compiling a kernel. I use buildroot, and buildroot has worked out really well for building not only just kernels, but many file systems, which I can also use to boot things up. The NVRAM, I implement this as an ini file. This is basically preloaded before I boot up the kernel. And then sometimes I have to make hand edits in the config files to match the QEMU environment, like especially network interface names and IP addresses, because eventually these emulated devices are also networked, because you can attack them remotely, you can fuzz them remotely. You should be able to play with it just like any other regular IoT device. The way the userland emulation works in RMX is that I have implemented a chroot environment. When I boot the kernel, I will basically boot into a minimal host file system. The host file system will just give me a shell. I'm not using anything specifically from the host file system. But inside the host file system, there is a chroot tree, there's a chroot directory, which basically contains the entire uncompressed file system from the firmware. And when I want to kick off the init scripts, I will have to manually kick off the init scripts from within a chroot environment. Right. Let's see how all this goes. And if luck holds true, you basically get your services working. Sometimes you may get errors. Like for example, if you emulate the IP camera, you also get to download a mobile app and you can view the IP camera remotely, as will all the predators in the internet will of course want to view the baby cameras remotely. But because this is emulated, you do not have a video device. You'll see like these little X's on where the camera should be. So there's some limitations. Not all drivers work. Not all devices can be emulated, but it's getting better with every version. All right. So now let me show you where we're at in terms of the ARMX architecture. I mentioned that we're using QEMU as a workhorse. The QEMU system ARM will be used to boot the kernel, which will be a matching kernel compiled using build root. The IP address is always hard-coded as 192.168.100.1 on the host system, which would be your Linux base that is running the QEMU. And the minimal file system that I boot up, hostfs.ext2, this is the build root file system. This IP address is hard-coded as 192.168.100.2, and it is mapped using the tap interface. So from the host, you get like you get like a network access, just like a virtual machine. But these IP addresses for now are hard-coded. The chroot environment is shown here in the dotted line, and this is mapped. Everything in the chroot environment is mapped in the /armx directory. The /armx directory, the tree is fixed. You'll always have a devices file in the armx root. You'll have a hostfs directory, which contains the hostfs.ext2, which is basically this image that is booted up. And then you have one directory per device. And each device directory contains a configuration, a matching kernel, and the unpacked root file system from the firmware. All this is exported using NFS, good old NFS, right, from the Solaris days, throwback to the 90s. And this NFS export is mounted under ARMX. So now you also get a little bit of host and guest sharing. Sometimes NFS is flaky, like there's some inode corruption, all that, but screw it, we survived Solaris, we can always survive this. Right, so let me go through this in a little bit. I'll give you a tour of ARMX for now. We have that kernel booted up. Let's see how that looks like. There we are. So let's see. Preferences, appearance, fonts. Okay, it's slightly better for you folks to read. So when you boot this up, this is the pre-compiled kernel, which is matching as close as I could get to the IP camera. So I could not get kernel 2.6.28 to compile because it's too old in the current tool chains break, the makefile breaks. I actually did get it successfully to compile, but I haven't updated it in ARMX yet. And this is built to emulate an ARM9 CPU, which is an ARM v5 core. I'm using the versatile proto board for emulation purposes. And then when it all boots up, you get the device console. At this point, it is analogous to the kernel being booted up, and you're now waiting to kick off the init scripts. At this point, I'm going to click the ARMX terminal, which basically launches, which essentially launches this this view. It gives you two choices. Either you want to be dropped into the debug shell. Let's see. Trying to right click and okay, it's not working well either. The magnification is not working. So you can either be dropped into the debug shell, which basically just gives you a bin sh on the device. And here is the bin sh. You can now take a look at the ARMX directory tree. I wish I could somehow make this larger. Yeah, there we are, preferences. Give me a moment. It's been a while since I've played around with the other we are. What's the system font? It's going to be give me a moment. Monospace. Didn't do anything. Sorry. No, there it did. Great. Yay. I'm able to do this. Beautiful. Okay. So inside the ARMX directory, you see, you basically see a lot of files. I have a devices file, which contains a definition of all the devices that I'm emulating. Then I have a QEMU options file. I have, and for each device that I've emulated, this is the D-Link router, this is the IP camera. I have a directory in there. I also have a template directory for which you can use to create a new device and the definitions based therein. I think somebody's trying to tell me something on Signal. That's not my message. I thought it was Dragos trying to tell me something. Okay, let me show you the devices file. Now the devices file is rather simple. It's just a CSV file, which contains a definition of all the devices. So each line corresponds to a device entry. You have the ID, then you can tell which QEMU version you want to use. Like sometimes I've found like in some devices, if you do an older version of QEMU, it disables the iCache. It is not implementing the iCache properly. But when I need to even emulate cache coherence problems, then I use a newer version of QEMU. Then you use which protoboard you want. So this is Versatile Express A9, any CPU specifications or memory, and which kernel you want to boot up. So these are all the custom compiled kernels. And then you have the label name, which ARMX shows you in the menu. So this is the devices file. Inside each device, let me show you the IP camera. Let's go to the try2227WF. Inside here, you have a config file, which basically provides specific information about the device itself. So I'm saying this is the try227WF device. There is no NVRAM. The IP cam doesn't use an NVRAM. I can point to a directory for the root file system. Basically, the root FS is what contains the extracted file system, a copy of the compiled kernel, which lies in the kernel directory. And then you have the init commands. So if you see, these are custom init commands that I've written. Basically, this happens after you play with the device for a couple of days or weeks. So first I'm faking a video device. I'm just creating a dev entry in the /device directory. Otherwise, the system does not proceed forward. Then I manually invoke rc.sysinit and rc init init.drc3, and then I just drop into a bin sh. If I look at the kernel directory, the kernel contains a Z image, which is compiled specifically for the versatile emulation board. And when I played with the device, I found out that the kernel does not support syscalls in thumb mode. So I've disabled syscalls in thumb mode for accurate emulation. Now, one of my big goals for ARMX is that if I find a vulnerability in a device and I'm able to fuzz it, triage it, debug it, and even do the exploit dev stuff and come up with a working exploit within ARMX, I should be able to use that exploit as is without any changes on a production IoT device, and it should work. So which means that I should emulate all the features of the kernel very faithfully. I should emulate the CPU very faithfully. Any cache coherence issues have to be emulated faithfully. And also the memory layout, like the memory division, 3 gigs, 1 gigs, 2 gigs, 2 gigs. Some of them have had like this 2.5, 1.5 gig division. Any oddities, any ASLR, non-ASLR, all that must be emulated really accurately. And only then, I mean, basically that's what you want. If it works on the device, it should work on the actual target. Right. So with this layout, let me now go into the presentation again. This is basically the directory tree that I showed you. There's a devices file. The run contains all the pathetically written shell scripts, hostfs, templates, and these are essentially your configs. All this is documented on the GitHub, and I've written some documentation about it. If you want to emulate your own device, there's some help that's given. So far what we've seen is we invoke the launcher parsed the device database and displayed the menu. From the menu, this is the menu that we got. We started the IP camera. From here, we basically booted the selected kernel. The network interface is ready, bound to tap 0, and the remote IoT device is now available at 192.168.100.2. And this is booted into the host FX with the ARMX directory tree NFS mounted from the host. Now we're going to invoke this is where we are. We are at the kernel boot up. Now what we're going to do is we're going to invoke the init scripts. To invoke the init scripts, what we can do is we SSH into 192.168.100.2. That's what the blue terminal does. And it gives you a choice. You want to enter the debug shell, or you want to now kick off the init scripts of the IP camera. I showed you the debug shell. Now what I'm going to do is show you the init scripts, and we will kick it off. So the init scripts will now look through the firmware, the unpacked file system on the root FS. It will then preload any NVRAM entries it needs to preload. It'll then create a chroot entry. It'll create a chroot jail around the root FS and then kick off the init commands. Let me show you how this is done. Okay, switch over to the live demo. We have this bit. Now we're going to invoke the launcher again. Here's the launcher. So start the TriVision IP camera. There's no NVRAM, so it's just telling me press enter to start. And when I do, it's now done the chroot stuff. It is remounting the proc file system. It's remounting the sys file system. It tries to load some drivers. The drivers complain because the symbols don't match. But eventually you see that all the init processes are started, and actually the system is now up and running. It is running the basic processes. We also get a BusyBox shell. If I now start writing commands on here, dumb stupid thing. Let me try, and if I run commands over here, you will see, you'll basically see all the processes are running. At this point, the device is actually booted up. So if I open up a browser and I open up a new tab and I now navigate to 192.168.100.2, with any luck, I should be able to, see the web interface of the IP camera. And if I now log into it, I don't get the default view. I mean, I don't get the video stream, but I can easily go to the settings. It'll give me all the IP options. I can play around with this. I can web hack this, I can burp suite this, I can fuzz this, I can GDB this, I can do whatever I feel like, because all the tools are available in the host FS. This is ready for fuzzing and exploit development. In general, if you want to do all this stuff on a real IoT device, you either have to like copy some statically compiled tools on there, you may have file system limitations, you might have to play some games and reflash the firmware with telnet inside it or some GDB versions inside it and whatnot. But RMX makes all this a lot easier. Let me go back to the presentation, show you some of the stuff with RMX. At this point, it is booted up. We can now do whatever we feel like with it. Let me explain you what the debug shell does. So with the host FS, I have also populated certain utilities that we'll need for playing around for static and dynamic analysis. We have GDB server, strace, ltrace, the usual suspects, netcat, lsof, socat, or whatever else you need, and a few scripts which are written to facilitate process enumeration and debugging and whatnot. So let me show you a demo on how I can attach GDB server to this. I have the screenshots of it, but nothing says awesome like a live demo, which sometimes fails in your face, but we've had enough of fail this week. Why not one more? Yeah. Let me leave the browser away. Let me minimize this shell that's booted in. And let me now go to the, let me go to another window now. I'm going to now use, this is basically AttackBox is my host. I'm not touching the emulated environment much now. I'm going to just leave this be. But I have certain scripts, like I can always do a PS on the device and find out the processes. Let's say I want to attach to this web server. Now, to attach to a remote web server, you got to do a GDB server, and then you got to do a host GDB. All that stuff is now really simplified with RMX. What you can instead do is you can just stay on the host. There are some RMX commands that I've implemented. You can write RMX PS, which will remotely SSH and dump all the processes. I say, okay, I want to now attach to the webs process. So I can say RMX GDB webs. So it will remotely invoke GDB server. It'll invoke GDB on my host, which is cross-platform multi-arc GDB. It will then set the remote directory to the correct chrooted environment, so it reads the symbols and all correctly. I also have Jeff loaded up to make GDB great again, of course, which shows me all these nice register and highlighted views. And at this point, I can continue and I'm ready to debug. I can now play all my usual tricks. Let's say you want to, well, of course, no demo is good without showing off an exploit. So let me show one off. Here's here's a base case crash. If you just basically do ipcam 0, it sends a very large URL and it triggers a crash. There's also a format string bug possible with it. Like if I do a IP camera, let me do that. There's a format string URL. So if I invoke this URL, it will leak out base addresses. This is how I used to initially try and get past ASLR until I realized that there is no ASLR implemented on the IP cam. So basically the format string bug is useless. Let me show this if I do admin. I found this format string bug by burp suite fuzzing, by the way. Let me cut and paste this gigantic URL in there. And now if I do you don't see anything on the screen, but if I do a view source, you see all these stack addresses leaked beautifully by the format string bug. So it plays, I mean, these will be the same addresses which will be leaked from a real device as well. Like, for example, here is a libc offset, which you see being leaked. This is a libc offset as well. So this is where I can get the addresses for the ROP gadgets that I need. Enough of all that. Let's try and see a real crash. If I launch this ipcam 0 at the target IP camera on port 80, we're now going to then switch to GDB. It drops out, but in GDB, now you get this beautiful crash. You get this program counter equals 41, 41, 41, 40. I now have a crash. If I dump some strings from the registers, I have some URL strings and whatnot. And at this point, I can now create a nice Stack Overflow exploit for it and own this machine. Let me do that. I detach this process. I'm going to restart the web server. So I'm just going to go back to the console and start webs. Bind to the web server again. And now I have a ready built exploit here. I have try-vision busy tell, which basically has some shellcode which invokes a telnet-d. I run telnet on the target, and then I should be able to telnet in to the actual system. I pipe this to netcat. I'm too lazy to write socket code, so I let netcat do all the dirty work. Pipe it in, and if I now do an armx ps, with any luck, you should see telnet-d is now invoked on the target. If I telnet into the system, I should be dropped into a shell. And essentially, yeah, this is how you can use armx to troubleshoot, debug, do whatever you want. This is a very quick and a rush demo, but I want to give you an idea of what you can do with it. And this same exploit works as is against the real IP camera, as I've done repeatedly, and some of my students who may be on this webinar would testify that this indeed works the way it should. So kind of trying to wrap up the talk over here. There are some slides over here. The slides are available on my slide share, and I'm sure Dragos will share them out to you folks as well. All this documentation is also available on GitHub, and I will share the URLs in a little bit. But basically, if you want to create your own device, the roadmap is first you make a new device from the template. Then you compile a suitable matching kernel. You have to suffer build root and all the invocations. Then you extract the compressed root file system, either from the device itself using 3 tricks that I will talk to you about. Create an NVRAM ini. If you've extracted the firmware, you may be lucky to get a copy of the NVRAM. If not, and if you've got a UART console and you can dump out the NVRAM using some command, do so as well. Then you have to play around with the config and the init scripts. And once everything works, you then create an entry in the devices directory in the devices database, and it will be emulated in armx. Yeah. Okay. How do you get the firmware? There are 3 ways of getting the firmware. The lame way is to get it from the web and FTP site, which is not that lame when you look at it. Any way is a good way. If it works, that's fine. But what happens with the web FTP default firmware is you don't get a copy of the NVRAM. You don't get a copy of the running state. and a lot of the configurations will be uninitialized. The best idea, my preferred way, is to basically look at the board, expose any UART interfaces there are, good old RS-232, connect using a serial console, and once you get a shell, you might have to brute force a password, or sometimes you just get like a root shell bound to it. Once you do that, you then lift all the MTD blocks by using DD and dump it or netcat it out or TFTP out, or sometimes these devices allow external storage. Like the IPCam allows you to put in an SD card, you then DD dev MTD block 8 and dump it onto the SD card. And that's how you get a copy of the squash file system or the compressed file system or the NVRAM kernel, whatever have you. And then you can put that into ARMX and emulate it. If not, this IP camera was actually a pain to extract because they had deliberately broken the received track in the UART header. So you can get all the debug messages, but you can't type any commands to it. Crafty jerks, you know. So, well, if that doesn't work, then what you do is you suck the firmware directly off the chip. And this is an A6 Forte. I wouldn't say the Rolls Royce of EEPROM programmers, but definitely a Cadillac. I don't care, whichever car you prefer is better, who gives a damn. But this thing extracts the firmware like as close to magic. You basically enter the number, the datasheet part number. You clip on the thingy onto the thingy over here, which is an SPI flash thing. You click a button in the software and the thing sucks the firmware straight out of the chip. In some cases, you might have to use a hot air gun and desolder the SPI chip and then suck the firmware, because sometimes when you power it on, the CPU powers on and it locks the chip. But in this case, it was nice enough to give up the firmware without having to desolder the chip. So once you have the firmware, then you just put it into ARMX. I already did the demo with you folks. So without further ado, here be the goods. The web page is on armx.exploitlab.net. You want to watch out for new ARMX announcements. Follow me at the real Saumil. I don't have a separate Twitter ID for ARMX. I am already terrible at tweeting and can't manage myself, let alone manage more than one Twitter IDs. If you folks are up to it, there is a nice IP camera CTF challenge. If you wish to download the preview VM of ARMX, and the TriVision IP camera is already emulated there, there's a nice little bug in there which you can play with and exploit. And if you write exploits for it and send me the write-ups, I will publish them and I'll give you some little goodie gifts. That would be. So folks, that's pretty much it with ARMX. This was my demo. I'll be happy to walk you through any missing pieces that I might have skipped through. At this point, the floor is open for question and answers. I don't know how we're doing question and answers. So let me see. I'm going to open up the chat window and see if there's anything that is asked. Okay.
I think we can we can do some question and answers. I'll unmute everybody. So if someone raises their hand, I'll unmute them.
There's one question on the chat room which I'm going to take up. Is this a similar capability as Lua QEMU that was demonstrated a few years ago to emulate ARM Wi-Fi baseband? This looks a bit more fleshed out, more of a framework, but without the scripting of Lua. So the Lua QEMU stuff was brilliant. Mine is unfortunately not as brilliant as Lua QEMU. I think what they did really well was emulate the hardware, the Wi-Fi hardware, the Broadcom hardware was very well emulated. That was, I think, the Project Zero folks that did it. But that was a super custom job. My whole approach is to make more of a generic environment for populating any firmware, throwing it in, and trying to get it started up. At some point, I would like to integrate this type of stuff. Will there be support of being able to run ARMX on x86 CPUs? Yes, yes. In fact, ARMX runs on x86. My virtual machine is x86. The preview VM is an x86 VM. Download it, play with it. Inside the Linux VM is a QEMU system arm, and this is what it's working on. What else do we have here? There is MIPSEX on the way. It is not even alpha. It is still in the minds of a few contributors. But yes, all we have to do is just play around with QEMU MIPS images. The same concept will apply easily. And then we can emulate all sorts of Internet of shit using MIPS. That should be possible. I haven't personally played with MIPS yet, so can't speak as to how soon we should have it, but some of my students did. So they're already working on it. I think with the self-file isolation, they'll be working even harder. More questions? Type it out on the chat window or shout it out.
Yeah, I got a question for you. Have you looked at RISC-V at all?
Have I looked at RISC-V? No. Who do you think I am? Don Andrew Bailey? No.
Nice.
I have not. I have not looked at RISC-V. It is on my to-do list, item number 873.
Just as a comment, it's a pretty cool architecture.
It is very cool.
Yeah.
In fact, I've been told that the Indian government is making RISC-V, RISC-V CPUs, and they're using it for some like promoting made in India type of hardware. It's actually pretty neat.
It's anyway, we'll have that conversation offline. It's got all kinds of interesting stuff.
Yeah, I see the AMIS website. The VMs are packaged for VMware only at the moment. Can we do it with VirtualBox? Yes, I'm sure. I just do not have the expertise with VirtualBox. If you folks wish to package it for VirtualBox, contribute it. I'll be very glad to host it. Coming from me, don't hold your breath for VirtualBox unless like Meltzer works on it or something. We'll do it some point, but it is way up in my to-do list because yes, I recognize VirtualBox as a priority. We'll get it done at some point, sure. Right on. What else do we have?
Going. Okay, a big virtual clap for Saumil.
Thank you very much. And stay healthy, stay safe. Thank you, folks, for doing this.
Thanks, Saumil. We'll give you a shout. I'll talk to you next week when the crater starts filling in, and we'll figure out other stuff.
We will do that, sir. Have a good.
Stay safe, healthy, and happy to you and your family.
Thank you, sir. Thanks, folks.
Hi, I'm Dragasuriu. I'm the conference organizer for PACSEC, CanSecWest, and the guy who started the Pwn2Own competition. We've been doing the PACSEC conference in Tokyo for the last 17 years now, since 2004. And this year, obviously, we're going to be moving it online. But we're going to be experimental. We've got some challenges in the online format, some limits to engagement and interaction, but we're going to be trying to overcome those challenges and take advantage of the opportunities, the freedom of accessibility, the lack of travel, the lack of venue restrictions and freedom for scheduling that we have in the online format. We're going to be doing VR meetings, live streams, stream out the Pwn2Own competition, and we're also going to be offering dojo training courses for the first time in a long time at PACSEC, taking advantage of the global accessibility that we have with this conference. At PACSEC Online this year, along with our new dojo training courses, we're trying something new, and we're going to be offering a free 2-day training course on September 23rd and 24th. It'll feature our dojo instructors giving excerpts from their longer dojo training courses, getting you some excellent free training on a wide variety of topics, and letting you get a feel for which one of our dojo courses might be right for you and your knowledge enhancement. Amongst the topics that we're going to have in our training courses this year include securing your legacy applications written in COBOL, effectively using threat intelligence, extracting and reversing firmware and writing ARM exploits, assessing and exploring your industrial control systems, developing exploits for the baseband processor in your phone using SDR attacks, locking down your Cisco networks and environments, assessing your IPv6 network security using the powerful scaping tool, making your security training more effective by making you a better trainer, attacking and defending your cloud instances and your Docker and Kubernetes containers. I hope we'll see you on September 23rd and 24th for this excellent free training, and later on at PACSec in November. Come sign up at secwest.net.